Hello and welcome. Today we're going to be talking about an example differential equation solution that involves a convolution integral and also pulsed forcing. So what we're talking about here, of course, is a Dirac delta forcing, which we call a pulse. Okay, so the standard model we always deal with is that of a mass that's on some skateboard wheels. It has a position x of t, and it's going to have a spring. We'll give this spring a Hookean spring constant of 4, and we're just going to have that as our dE. So when we have that, we're going to get x double prime plus 4x is equal to, and then of course on top of that, we're also going to force our mass spring system with some sort of force. The specific force that I want to force this with is actually a delta function, a pulse that happens at time 0, and then I'm also going to subtract to it another pulse that I'm going to give it at t minus t naught. All right, here I'll say that t naught is positive, okay? So just to label this is going to be a pulse at time equals 0, and here this is going to be a pulse at some later time. Okay? All right, so we expect basically this mass spring system is going to... the other thing I should say, though, here is basically this is going to be a positive push. And here, this is going to be a negative push. So basically opposite direction. Okay, so one question I might want to ask is, so we'll also assume that x of 0 is equal to 0 and x prime of 0 is equal to 0. So we're basically at rest. Okay, so we're at rest here while we're before the push, but then after the pulse, we expect we're going to have an oscillation. All right, but after the second pulse, what we like to ask is basically, is there a T naught that stops all motion after T naught? So that's what we're going to ask. Basically, we're going to solve for the T naught such that x of t is equal to 0. There's no more motion for t greater than or equal to T naught. All right, so that's our problem. What we're going to do to solve this problem, so what we have here, though, of course, is a differential equation that models a mass spring system. There's no friction in this system, so we expect sinusoidal oscillations. But what we're going to do is basically give it a positive push at the initial time, and it's going to get the thing going. And then we're going to knock it in the opposite direction at a well-timed T naught that will stop the system at a later time. All right, so let's see if we can figure out what this looks like. So of course we're going to use Laplace transforms. So we have x double prime plus 4x is equal to f of t. And I'll just put this to be generic for now, okay? Of course, we know the solution is to use our Laplace transform on the whole thing. That becomes a capital F of s of t, or sorry, capital F of s, and that becomes s squared capital X of s plus 4 capital X of s. Capital X of s, we can factor it out, and we get the following. All right, and we call this, of course, the transfer function multiplied by our forcing function. So the key here, of course, is we're going to find the inverse Laplace transform of t of s. which we're going to call kappa of t, and that's the kernel, or Green's function. Those are the two words we often ascribe to that. And this, of course, we call the transfer function. We call that the transfer function. And what we're going to get, of course, is x of t is equal to the inverse Laplace transform of not x of t, I'm sorry. That was going to be our kappa of t is 1 over s squared plus 4. Okay, so we can look at the table. Look at the Laplace transform table. Okay, we note, if we look at many Laplace transform tables, we see this one, that the Laplace transform of sine of k of t is equal to k over s squared plus k squared. So I'm looking up here, and clearly I see that if k is equal to 2, then that means we've almost got it. So what we can do here, of course, is I'll move down here. So if I take my Laplace transform that I have, and I'm taking the inverse now, and I have a 1 over s squared plus 2 squared. And what I got to do, of course, is get that something like that k. I got to figure out how to get a thing like k that's up there to fit the template of the Laplace transform table. And what I can do, of course, is multiply by 2 and then also divide by 2. And use the linearity. And again, what we're doing here is we're taking the 2 and then moving it outside of because the scalar multiples move through the inverse Laplace transform. And now we have it. What we get is, of course, 1/2. That's the 1/2 on the outside is sine of 2t. And that's going to be equal to our kappa. All right. So using that result, we recall that basically x of t, the solution to the dE, x double prime plus 4x is equal to delta of t minus delta of t minus t naught with the initial conditions equal to 0 is expressed via the convolution theorem as x of t is equal to the integral from 0 to t of kappa of c times the forcing of t minus c d c, where c is this Greek symbol. And I prefer this Greek symbol just because it's kind of an ugly, it's kind of the ugly duckling of the Greek letters. And it's easy to recognize as a variable of integration. When we're all done with our integrals, there'll be no more c's around. So it just kind of helps, orient ourselves when we're working on these integrals. So of course, we need to note one more thing, of course, that if I have, the key thing here is the delta functional. If I integrate over a delta functional like that, over some domain, I'll call that S, it's going to be 1 if 0 is in the domain of integration, and 0 if 0 is not in that domain of integration. That's the key identity for delta functionals. Okay, right? So when I write my x of t like this, what I'm going to do is write it as 0 to t of, and we had it now as 1/2 sine of 2c, like that. That's our kernel function. Okay, and now we're multiplying it by a delta function at t minus c, and then also minus t minus c minus t naught dc. So we have to do, and we also have to note another identity, of course, which is if I have an integral from 0 up to t of, let's say, some function f of c, and then if I have a t or a delta function, also c minus t naught dc, this is going to be, of course, it's going to be equal to f at t naught if t is greater than t naught. Here we'll assume here that t naught is greater than 0. And it's going to be equal to 0 if t is less than t naught. And the idea here is that this allows an integral to serve as a way to evaluate a function at a specific point, which is a pretty cool identity. Okay, so that's going to help us figure out what to do. Okay, so with that, what I'm going to do is I'm going to go to the next line here, or next page, and rewrite what we had before. And see what we have here is actually a t minus c minus delta, and we can write it as t minus t naught minus c dc. So we could also note that if I have some integral from 0 to t of f of c of any delta t minus c dc, that's simply going to be f at t. Okay. So, and that's just using the identities of the delta function in a slightly different way of expressing it. So if we go down here, we should be able to take the 1/2 out, the integral from 0 to t of sine of 2c delta of t minus c dc, and now we're going to break up our integral into two components here. Okay, and what we can see is the following. We're going to get 1/2 times sine of, and now what we do, of course, is what the integral says is basically we're going to evaluate at t right there. So we're going to get 2t. Finally, here, it means we're going to evaluate that function, sine of 2c at t minus t naught. Okay? So we're going to get a minus 1/2 sine of 2 times t minus t naught. Right? And this has to be then, of course, what we have to do, though, of course, is that we have to put a Heaviside step function on this, though, at t minus t naught. And the reason, of course, is that we have to have it so that our basically this turns on only after t is greater than or equal to t naught. Okay. All right. So our goal was to find a well, before I get ahead of myself here, what I'm looking at here then is the x of t is going to look like this. The graph will look like this, right? At time 0, we're going to get an oscillation like this, right? And we're going to go up to positive 1/2, and then, of course, down to negative 1/2, and that's just going to be a sinusoid. And we're going to go through over an interval of length pi. We're going to go through, over an interval length of pi, we're going to go through one cycle. Okay, so that'll be 2 pi there, 3 pi, right? So the question is then, if I put a t naught somewhere, how can I get it to stop? Where do I put this t naught? Do I put it somewhere? Somewhere we have to put it so that we can stop this oscillation from occurring with the well-timed pulse. Well, if we look at our answer, I think we can see it pretty clearly. So when t is greater than t naught, we're going to have x of t is going to be equal to the following: 1/2 times sine of 2t minus sine of 2t minus 2t naught. All right? So sine of 2t. So what we need to do, of course, we need these two to cancel. So we ask basically what t naught makes those cancel. Of course, we know that sine of 2t plus 2t naught will equal sine of 2t when 2t naught is equal to, well, 2 pi, 4 pi, 6 pi, and so on and so forth, right? So, so that means, of course, that t naught can be either pi, 2 pi, 3 pi, and so on. So at any point while the system is, so we can see basically as the oscillation is coming up at all of those multiples of pi, at any one of those points, if I have a downward pulse that goes in the opposite direction, we can stop the oscillation cold. So to redraw our graph, so let's pick a specific value. Let's say we pick t naught to be equal to 3 pi. We're going to pick that to be the thing. Then what is our answer going to look like? Well, it's going to look like this. My x of t function, which I said was 1/2 times sine of 2t minus sine of 2t minus 3 pi. And then we have to put a h of t minus 3 pi on there, a Heaviside step function, like that. And the graph is going to look like this. We have 1/2 here and negative 1/2 here. So of course that was the first oscillation, the second oscillation, and the third oscillation at 3 pi. And at that point, after that, it's all going to be 0, because while we had some forward momentum going that way, so here we had a pulse that started our oscillation. It started our oscillation. So before that time, if you can imagine that time, we had no motion in the system at all, and we gave it that positive pulse, and that got some forward momentum going, and then the oscillation just would occur. And now here at 3 pi, so this is our t naught point, we have that forward momentum, that upward momentum, but now we're going to give it a negative pulse, and that will stop the system cold. Okay, so this is just a good example of how to use the convolution integrals, how to use delta pulses, how to look at all of that stuff so we can start making, constructing solutions of differential equations for forcing that involves pulses and discontinuous pulse forcing and things like that. So hopefully this was a fun video to kind of just see how to use the convolution integrals and delta functionals, all in some concerted way to accomplish a specific task. All right, thank you so much.